Hello and welcome to PML School. Today I'm presenting a PKPD model that I've set up in non-mem and Phoenix NLME for comparison reasons. So what we have is a simple one compartment IV infusion model, and we want to link that with a full Emax model that has a baseline and a shape factor. In this particular example, we have to deal with hysteresis, and that is why we use an effect compartment to model the delay between the PK and the PD model. As with all our previous sessions, our focus will be on hands-on training and not on teaching the theoretical concepts. So I will explain how the original non-mem code is translated into Phoenix NLME, or better PML code. I will also briefly present how you can set up the same model without any textual code, just by using the built-in tools that are available in the Phoenix model object. And as always, while I'm going through the presentation, if you have any comments or questions, just use the Q&A panel on the right-hand side of the WebEx console. Moving on, here's our agenda. As usual, we start with a brief model description and then go into exploratory data analysis, looking at the plots, as well as to the input data that we need to use for the two models. And then the biggest part is the description of the model in NMTran and PML code, where I walk you line by line through the different codings. Then we got to go to a demo where I walk through all the modeling steps, and at the end of this I'm summarizing, and we'll go into the Q&A session. That's our agenda. Let's move on. So what is the model? Here, once again, in more detail, we have a central compartment for our PK, to which we apply a single IV infusion of 100 units. And then we have an Emax model. It's an inhibitory Emax model with baseline and shape factor. And as I said, we also have an effect compartment. For the error model, we are looking at the effect observations only, so the responses. Here we use an additive residual error model with an initial standard deviation of 10. Coming to the structural parameters, we have volume and clearance for the PK. This is actually already given, so we are taking the results of a previous PK run. So there was one compartmental model that was fit to the concentrations. So we have volume and clearance, and since we are using a slightly different parameterization, we will convert that into a microconstant. But I'm coming to this when we look at the code. Next one, the PD, we've got 4 PD parameters, E0, the baseline, Emax, the maximum response, EC50, the concentration of half maximal response, and gamma, which is the shape factor. Then for the effect compartment, we have KE0, the distribution rate constant, and VE, the volume of the effect compartment. So these are the structural parameters. We only have one random effect where we set an initial variance of 0.05, which is roughly about 20% population variability. And typically we use the FOC ELS engine, which in non-mem terms means FOCE with interaction. So this is this model in brief. Let's have a look at the data. So here's the plot of the first profile. So you can see that we have a baseline where this starts, where the drug is swallowed, is infused, sorry, between 150 and 200. And then it drops off sharply, goes over into a plateau phase. And after 50 time units, it steadily goes back to baseline again, which is, it reaches at around 200 time units. So we only have effect measurements over time. We don't have any concentration measurements. As I said, the PK parameters were estimated in a study beforehand. And the PK model was fit, so we only need to deal with the PD parameter and the effect compartment in this example. And this is a typical approach, a sequential PKPD approach, where you start with PK and use estimated PK to fit the PD. Next one. We need an effect compartment, and the reason is displayed here. I've used the actual PK model and the fitted parameters to calculate concentrations for the time of the observed effects. So I'm plotting here the concentration versus effect over time. The concentrations over effect, and lined up for the time of the measurement. And the concentrations are really following a hysteresis curve. So there is a delay between the PK and the PD, which we have to model. And a typical way to model this delay is using an effect compartment. And I will show you how to do this in textual mode, but also with a graphical model in NLME. Next, we are looking at the input data, and we can use the same sheet for both for the non-mem input as well as for the NLME input. And we are starting with an ID column, just a subject identifier, which we need for population modeling. Next, we have AMT, that is the dose amount, and rate is the rate of infusion. And then, as I said, volume and clearance. These are the post hoc estimates from a previous PK run. So there was concentration data and one compartment IV infusion model that was fit to those concentrations, and the resulting parameters are volume and clearance, and these are just post hoc estimates from that run. Then, of course, we have the time column here, the effect, that is a measured response. We also have an MDV column here, which just indicates whether the record is for dose, like this one was 1, or whether it's a true observation, which is 0 in those cases. So this is the input data that we use. Next slide. Yeah, next slide. So we are coming to the model code now. And it always adds some non-mem and NMTran records with the input. With the definition of input, and you see all those columns that I've just talked about are read in here. Effect is the dependent variable stated here. And as a subroutine, we are using advent 6 with a tolerance of 3. This is set up for differential equations. And for the model, we have 2 compartments, the central compartment and the effect compartment. On the right-hand side, we typically do not need to specify the input for Phoenix and NLME, since we have the graphical mapping panel typically where we assign the input data to the required parameters. But here, since we are using a textual model, we need to read in the 2 PK parameters from the input. And this is just a simple trick. Whenever you want some additional input to be used in your textual model in LME, you can use the covariate statement, which is shown here, and enter the name of the columns that you want to use. This is then being shown as an additional mapping option in the main mapping panel. The second line just defines where the dose is being applied to, and here it says that the dose is directly applied to the central compartment, so it's an IV dose. Next slide. So here are the differential equations, and the syntax is shown here on the left for NMTran, for non-mem. So the change of amounts in the first compartment over time is given by the amount that is transferred from the second compartment through rate constant K21 minus the actual amount in the first compartment times the sum of the elimination rate constant K10 and the distribution rate constant to the second compartment K12. Similar to the differential equation for the effect compartment, the second compartment is much like a peripheral compartment, if you will. The effect compartment is just made up by the amount of from A1 that is transferred to the effect compartment minus the other way around, I mean the distribution back to the central compartment. And syntax in NLME on the right-hand side shows similar equations. It just uses a little bit more text rather than these shortcuts here, but also in microconstants K21, K10, and K12, and everything in parentheses of the deriv statement. The deriv statement is used for expressing differential equations in NLME, but it's really much the same. Next slide. So we need to define the structural parameters. So we do that in non-mem. Here, I mean, you see V and CL, volume and clearance, are defined in the input data stream, that's clear. But as we want to express our model with microconstants, it just shows you how to get from clearance volume to the elimination rate constant just by dividing clearance over volume in the central compartment. Then we have all the PD parameters. You know, this is just an assignment of the PD parameter. This is a structural parameter E0, the baseline. This equals the first fixed effects, theta 1, and so forth, Emax, C50, and so forth. And the only structural parameter for which we allow a random effect is actually the C50, where we apply this random effect eta 1. Other than that, it's just assigning structural parameters to the fixed effect theta in increasing order. Then we have an initial estimate for the volume of the effect compartment, a very small value, and we just give the microconstant from the differential equation, so corresponding name K21 equals KE0. KE0 is estimated and then used in the differential equation as K21. Similar with V2 and VE, these are exchangeable, and then we have to express our K12 constant as a combination of K21 with the relation of the two volumes V2 over V1. And when you look over to the right-hand side, you see essentially the same equation. Nothing has changed. The only thing that is really different is you have to enclose the structural parameter definitions with the ST-PARM statement in PML. But that's it. The rest is just the same code. Okay, then the next one is theta and omega, the fixed and random effects. This is the matrix here for theta, just theta 1, 2, 3, 4, 5, and the initial estimates are set for E0 and Emax. For C50, we are applying some boundaries. So in this parentheses are enclosed first the lower boundary for this estimate, second argument is the initial estimate, and third argument is the upper boundary. So this is for C50. Similar 0.1, 2, and 10 for gamma, and 0.2 and 1 for KE0. We only have one random effect, so the omega shows one initial value, 0.05. The syntax on the right-hand side for NLME is a little bit different, so we put everything into the fixed F statement. And here we just need to name the fixed effects, in this case theta 1, 2, 3, 4, 5, and then as kind of a vector expression C, which encloses the same kind of three arguments that you specify here for non-mem on the left-hand side, so lower boundary, initial estimates, and upper boundary. But for NLME, we are really trying to avoid putting any boundaries. on the fixed effects, since the algorithm should handle this without any boundaries set. And the random effect is specified in PML using the random statement. It's a diagonal block, okay, it's just one random effect, eta 1, and that is initially set to 1. Finally, this is the last part of the textual code, the specification of the residual error model. Before that, there are some scalings, if you will. The concentration, we want the program to calculate the plasma concentration. That is done by scaling the amounts with V1, the volume of the central compartment, or the effect concentration, which is scaling the amount in the effect compartment divided or scaled by the volume of the effect compartment. And then we are expressing, you know, the effect, which is the Hill equation, E0 plus, you know, this equation, Emax minus E0 times C to the raised to the gamma divided by C50 raised to the gamma plus CE raised to the gamma. And then there's the description. This is the expression for the additive residual error model. So the prediction is the best prediction. The observation Y is the best prediction plus an epsilon, the residual error for which the initial estimate is 1. Same kind of equations on the right-hand side with NLME. C is central amount divided by V1. CE is effect compartment amount divided by VE, and the same kind of Hill equation. For the specification of the error model in LME, we use two statements. First, the error statement, which gives an initial estimate for the standard deviation of the residual error, EPS1, and then the observed statement, where we say that the observed value is the best prediction plus C, epsilon plus C, the error. So this is all the code. And moving on, I mean, this is when you enter this code into the program and you link it with a data set, you should be ready to run. But let me show you one thing. If you're not that comfortable using textual models, for this model, you don't actually need this. You can set up the whole model using the built-in function of the Phoenix model object. So here are the steps to get you there. So first, you switch the type of model to PK Emax. Then we switch to micro-parameterization. By default, it's clearance parameterization. And we activate this box infusions possible because we are dealing with IV infusions. But you leave intravenous and number of compartments as is. Next, since we don't want to fit any PK part, we want to freeze the PK parameters. And then for the effect compartment, we need to switch this on to allow for this effect compartment. And for the Emax model, we use all the full baseline inhibitory and sigmoid functions. And on the right-hand side, you see the corresponding formulas. They look a little bit different to the code that we've just seen, but don't worry, I mean, these are really the equivalent codes. And this is just a graphical representation of the this one compartment IV infusion Emax model with baseline and shape factor linked by an effect compartment. So you have the PK block here, central compartment, elimination compartment. And then moving over to the link, the effect compartment that is going into the effect block where we have some observations, effect observations. Okay, with that, I guess we are good to go into the demo. Let me share my Phoenix. Okay. Sherry, can you see that?
Yes.
Okay, good, thanks. So for this project, we have this input sheet. I showed you this in the beginning. This is the 8 columns that we need to use, IDs and so forth. And we have the code. Here's the control file for the non-mem execution, which we just went through. And here's the corresponding part of the PML code, an NLME model. In order to use this, we just send our input file, in this case to a non-mem shell. Just put it into the standard workflow. So here we have the input file. As a control file, we just need this one, trend code and a trend code. And so this should be now ready to go. So all the links set. Just this one. Okay. And off it goes. So it will take a control file and compile the model, and then it will run a few iterations to come up with some final estimates. What is going on here? Oh, you're not responding. So while this is still working, I've got these models already prepared, so we might look at the preparation. Oops, no, it doesn't like me today. Just a second. So the lockware is not responding. There seems to be a problem here. This is a demonstration bug, I guess. Come on. No. It doesn't like me. Let me stop this here. Let me go back. Yeah, sorry for this. This is obviously something happening in the back that it won't let me run this model. Let me take this. Class program. I need to just restart it, and then I'll walk you through the individual steps here. Once again. So let me load this file. Then I can share the application once again. Okay. So I've prepared the run already. So this is a non-mem shell. So we have the PKPD link file and the corresponding control file. And what you get when you run it properly, don't know what happened in this test. You've got your theta table with the final estimates, summary, and so forth. And this is something we can also do with a Phoenix model. Here again, I guess we have linked the input here in the mapping panel. You see all the columns here are being mapped. And the model code is here. It's the same as we have put here in the code, PML code file, and that is being executed. And then you get to the theta table, the final estimates, standard errors, CV%, and so forth. One thing you want to see actually, and you know, this is just using the PD data to fit in. So what you get out of this is mainly, let me show this here. This is a residual, conditional weighted residuals, the ETAs, CVRES, CWRES versus IVA and PRED, and then these, effect over time fits that you see here, also on a lattice, right? But what you don't see, you don't have any concentrations. But as we know, the concentrations are being calculated. So what you can do in this case, you go under Run Options, and you specify just an additional table. You just add a table, specify the time points that you want to use for the calculations. So it's a sequence statement with initial, endpoint, and the resolution, one per time unit. And then as a variables, you want to see the concentration, the effect concentration, and the predicted response. And then you see a table like this one in the output, table 01. This is the ID, the time, concentration, CE, and TY. And obviously, you can send this to a plot, XY plot. Let's put it into this plot, Ryan. And then you, for example, you can, no, it's the other way around. TEY versus C. What you get here is this kind of plot. Wait a second. We need to do a page sort by ID, so that you have for each ID the profile on a separate page. Then you've got something like this, where you actually should unsort the values, and maybe we also don't need a marker. And here you see the hysteresis curve. Maybe you can see it better with it this way. Okay, these are the hysteresis curves for these 8 profiles. And so this shows the delay, but if you want to see the effect site concentration, then you see all the time, let me uncheck some markers, it's a kind of sigmoidal curve of effect, concentration versus effect. So this is really showing that the hysteresis loop collapsed, more or less, which we want to have in our final PKPD model. So this is just an additional output that you can generate, not only here, but also for non-MEM. You just need to put it into the code, and then you can generate these kind of graphics. What I typically do in order to compare these outcomes from non-MEM and Phoenix and LME is to apply this comparison workflow, where you can then create eta worksheets, theta worksheets, overall omega and residuals, and all the plots, so that you have the information next to each other, side by side. So what you need to have here is obviously the data links. You link all the individual files from your output into this diagram, and then you can, for example, prepare your theta sheet. This is done in several steps where you can append, stack, and join and prepare values in order to get to the final results, which is a table of the form of this, where you've got the NLME estimates and here on the left hand and the non-MEM on the right hand side, and you see and compare the values. These are very, very close to one another, so it's really a close fit between those two. The same you can do with the etas, right? So you can prepare the etas, and then you have the etas also side by side, like here. And again, I mean, the results look pretty similar. But interesting is also the residuals, because for the residuals, you can then, on the basis of the residuals, create a bunch of outputs, of plots. For example, the conditional rated residuals here as a histogram, the eta as a histogram, then CWRES versus IVA. Do you see this looks much the same between NLV and non-MEM, also here versus PRED, DV versus IPRED, and the log version of this. And here are the fits in one shot, on one plot, NLME versus non-MEM. Also here you see very high similarity, but you can also compare it obviously on a lattice, so that you can really look at the individual plots and so forth. And finally, you put everything into a reporter tool that you can then save as a Word document. So this is actually the PKPD model, executed use model with the Phoenix NLME and the NonMem program. And there's also a possibility to use a built-in model. And you can do that by just taking this PKPD link and send this to a Phoenix model object, and then just put it into the whole into this workflow. And here we just need to do a couple of switches. So we switch the type to PK Emax. In this case, we'll stick with the clearance parameterization. I'll show you why. Intravenous 1, and then we don't need a closed form. We want to run it with differential equations. Infusions possible, and we want to freeze the PK. We have an effect compartment, and we have an Emax with this baseline, inhibitory, and sigmoid. So this is specification of the model. And now we need to do the mapping here on the top. ID is ID. The amount is A1. The amount for the central compartment rate is A1 rate. And then the effect is EOPS. Now what we have here is a very interesting situation. We have a POP PKPD model where we are using, for the parameters, for example, the structural parts, we only want to use the random effect on the IC50, right? And the rest are just the typical values. But we want to combine this with parameters from a previous PK run. And these are post hoc estimates. So these are expressed by a combination of the fixed effects and the random effects. For each individual, you have a different set of volume and clearance values, right? And this is now the problem with, I just call this built-in model. What you can do now is you can't do exactly, import, use these post hoc to combine the post hoc parameters with the POP PKPD model, because it would be a mixture of individual fits for the concentration and a population fits for the PD part, for the effects. So what you can do, typically what you do is a parameter mapping. You can include parameters here, but if you do that and you really want to maybe adjust this built-in model, I call this individual, right? And you can switch population mode off and use the ID as a sort variable. And then you can actually use the stacked, I've just stacked up the estimates for volume and clearance in this stacker object, and I use this as my parameter input, so I can just put it in here, say sort by ID, parameter, and initial as estimate. Then I need to provide some parameters mapping. So the program knows how to link those in the model code, and you can just need to make it a little bit bigger. So clearance is a typical value for clearance, and volume is a typical value of volume. So this tells the program what to use in which case. Okay, and then we can actually run the program. So. Okay, this will take a while because there's now an individual fitting, not a population fitting. I'll come to the population fitting in a minute. So, but just to show you, what you can do in principle. So here now you see at the theta worksheet, you got for each individual an individual set of parameters, for which the PK parameters are obviously frozen, but the PD parameters were estimated. You get to the same kind of graph plot. The fits look reasonably like the others for the population fit, but you don't have a population fit from this. If you really want to do a population fit, copy and paste. I just call this maybe to pop one. Let me do this. What you do with, I mean, obviously, first of all, we need to check population box. We need to get rid of these and these. If you would have the random effect, I would use the random effects from your previous PK model and link it in here. Then it will take care of the post hoc step on its own. But I don't have the random effects from the previous PK model. All I have is just the PKPD link data that was provided with the original model. So this is the way I can't do it. What I could do actually is, what is the warning saying? I missed my. This is done. Okay. What I can do is I can include covariates from the table, like volume and clearance. I can add those, right? And I can say these are my V individual and clearance individual data, right? So, and you see it's showing up in the main mapping panel, and I just need to do the mapping so that the program understands where to look up the data. So this is now the data has been looked up. So let me go further. Now we go to the model. This is still the model, but I need to insert, oh no, wait a second, I need to go to the micro parameterization because I want to have this KE expressed here, and I'll show you why. So now I can switch this to the graphical model, and I can insert a procedure. And what the procedure is doing is it should take as KE CL int divided by V int. So it is calculating KE by this procedure, by the red in values for CL individual and volume in individual. And then you see I can link the KE with this KE. And I can also insert another procedure. This is necessary for V equals V individual, right? And you see V is now expressed as V individual. And now this is all I need in order to run this as a kind of a population model. Still showing me must not main columns. Oh yes, sorry, I have that. And now I can just give it a start. And it will run so. Okay, so these are the different options that you have. Maybe a little bit, yeah, and here we've got our plot. Oops, no, it's not fit. I guess we didn't provide good initial estimates for these. I see, okay. What did we have? Emax was 120, E0 at 180, TV EC50 was 0.5, and this was, I don't know, 0.2. Let me run it once again. Okay. Okay, this looks much better. Yeah, the initial estimates, yeah, we're missing. That should be okay now. Yeah, and here you see the fits, much the same as before. So, and our theta values are here. Okay, this looks good. Okay, with that, I guess I'm at the end of my demonstration. Let's move on. Brief summary. So we had a PKPD model, which we've used in a sequential mode. So we have already had an established PK model, and then we applied it to fit the PD model part. So these are the plots from this PKPD model, which you saw the fits were pretty close, and also guided by the, also shown by the theta table here, where you got really very close fits between the two different model outcomes. Okay, with that, I guess that's the end of the presentation. Let's go to the Q&A. As usual, Cheryl, I don't think I can see those questions. Do you see any?
There is one. There is one from Jane.
Yep.
He says, can you set different PK parameters for individual subjects and then do PD fits with a population model?
Yeah, this is something that I tried to show in the demo. If you have random effects for these individuals, it would be straightforward to add those, to link in those to the model object, as you've seen, right? Otherwise, you would need to work around this by introducing these post-hoc estimates as covariates that you can then introduce into your model, like what I've shown, that you switch to the graphical mode, enter some procedures, which is just equations or assignments, if you will, and then you assign the individual parameter estimates to the parameters in your model, and that will give you the options to run this individual parameter estimates within a POP-PK model, PKPD model, sorry. Okay.
Okay, that is all.
All right, thanks, Cheryl. Then I guess before I close, just a few words of what is coming up here at PML School. First, we will have a long summer break, as you can see here. So we are closing the school from July to September, but we are coming back in fourth quarter with some additional non-LM NLME comparisons. I've so far planned 4 sessions, but I don't know. These models are getting more complex because we are dealing with more difficult data and needs more time for preparation. But we will get back to you and provide the new schedule soon enough, so you can make a link and note in your calendars. But to stay up to date with those events, unfortunately, due to new legal, new legislation on how to get in touch with our customers, I'm no longer able to send out invitations by email. So what we need to do in order to keep in touch would be 2 options. One is to use the LinkedIn group that I've created, the PML School LinkedIn group. I've shown you the link here. Or if you don't have a LinkedIn account, please watch the landing page on Certara.com, where all those events will be shown as well, together with registration links. With that, I'm at the end. Thanks for your interest in PML School, and I hope you stay in touch. And yeah, with that, I'm at the end, and goodbye, and you may disconnect now. Thank you.